Welcome to the demonstration of Alphacapture, the CCD-based polychromator spectrometer. In this video, we will show the application and performance of Alphacapture. The device shown in the video covers complete range from 200 to 1000 nanometers of spectrum with resolution of 1 nanometers. Alphacapture takes less than 1 second to record and transfer the spectrum data to the host PC running the analysis software. Alphacapture is designed as a modular platform, which allows flexibility and diversification of applications. For this demo, we will show 3 attachments as 1. Cuvette holder, 2. Color scanner, 3. Optical fiber. Cuvette holder. The cuvette holder attachment can be used to perform molecular analysis of liquid samples. The attachment contains integrated light source, such as tungsten, or micro-xenon lamp. Using this attachment, the system can compute absorption and transmittance of liquid samples. Color scanner. The color scanner attachment can be used to record reflectance of solid samples, such as powder, textile samples, food items, toys, paints, etc. Optical fiber attachment. The optical fiber attachment can be used to record spectral data of light source, or can be converted the system into Raman spectrometer, HPLC detector, or any similar device which needs to record real-time spectrum. Once the application is launched, the user is shown various application mode of operation. These can be made custom for OEM or scientific research partners. Let's dive into the color scan application. For demonstration of this mode, we will be using some samples, like colored paper, paint sticks, solid plastic items. Here, we have a colored sticky note with this color. We will now run a scan on the sticky note paper. Note that the system shows lab values with the spectrum and a representation of color being scanned. The color scanner attachment ensures that the object is always aligned perfectly with the system. To give reproducible results, we will go ahead and save this data with a suitable name. Similarly, we will scan the multicolored stick and save its data as well, as the stick has different colors within close proximity. Thus here we show the accuracy and size of the capture window of the attachment. Again, we will save this data for future analysis. Now we will scan a solid object, which is almost impossible to be scanned in conventional system. We will go ahead and save this data with. As of this point, the system's database had no references of the samples shown above. However, once saved, the system automatically scans the database to find the closest color match, thus optimizing the process as a user may have hundreds of samples saved in the database. Now let's scan the sticky note again to see if the system can automatically find match from the database. The system has pointed out a match, and also selected the same. User can disable the auto-matching functionality, and select a sample directly as well. Note that the difference is shown as 0.366. This is the delta E parameter which is used to find the difference in lab values. Let's record another scan, to see the repeatability of the system. The new result shows a difference of 0.44, which is well within the specifications. Now let's scan a new sticky note from the same batch, as it will likely to have a slightly greater variation in color match. The system again matches the sample from the database, and the difference is shown as 0.93. The matching tolerance can be set into the software. Now let's scan the solid plastic pen to see the color difference. As seen, the difference is shown as 0.89, which shows the outstanding result reproduction considering the object is not flat and has contours. We will now attach the cuvette attachment, and the light source integrated within the attachment can also be seen. We will be using Titanium-based SRM from Helma to show the demo. Let's head back to the application and select Spectrophotometer application. In this mode, the application allows user to record photometric data, quantification, wavelength scanning, kinetics and other modes, which are available in classic spectrophotometers. Also the software is CFR 21, Part 11 compliant. Let's see the photometric performance of the system. We entered the desired wavelength and perform the blanking operations. Let's put back our sample and see the absorption of the SRM. At this particular wavelength, the result matches with the certified value of the SRM. Let's take multiple reading to see the repeatability of the system. We can see the repeatability within third place of decimal, which shows the high performance characteristic of the system. Now let's perform a full spectral scan of the sample from 400 to 900 nanometers. Let's set the parameters and perform baseline and then analyze the SRM. Notice that the complete scan takes less than 1 second, which again shows the extreme performance of the system in this mode of application. The graphical data can be selected to view a particular region of interest. Also, the data is available in tabular format. Here we see the peak data from the result. Notice that the scan shows a value of 0.322, which was shown as 0.323 during the photometric test. Thus the wavelength repeatability parameters is also within class-leading specification. We will now attach the optical fiber attachment and capture the spectrum of a neon SRM light source. As seen here, the peaks are resolved within 1 nanometer's spectral resolution, with the wavelength scale on the x-axis, and the arbitrary intensity scale on the y-axis. This mode provides advanced options to the user to set custom integration time, apply data post-processing, calibrate the system with multiple sources, etc. With this, we conclude this demonstration of Alphacapture system. We hope that this demonstration was able to answer your question around